Hi everyone, how's it going? This is Sasha from C's AI. In this video, I want to talk about two popular predictive machine learning models, XGBoost and CatBoost. So in this video, I'm actually going to start by giving you some of the technical background behind how these tree-based models work, what their key similarities and differences are, and what scenarios you should apply which one. Then after that, I'm going to show you a Python tutorial about how to implement both CatBoost and XGBoost and train them using your GPU, and also how to do hyperparameter tuning at the same time in a very efficient way. And then at the end, I'm actually going to do a little performance test to see how CatBoost and XGBoost compare when you try to apply them to a real world scenario like a Kaggle regression prediction competition. So let's get into it. So first, like I said, I'm going to talk about some of the technical background. And a few weeks ago, I actually made a video where I talked about how simpler machine learning models can actually be more effective and efficient depending on the type of task you're trying to solve. I know that might sound crazy in the current AI market where all the hype is going to, large language models, which have hundreds of billions of parameters and take thousands of GPUs to train. And people have been really talking about chinchilla scaling laws and how that's kind of like the overarching theme where everyone's saying that, model's performance is going to improve linearly with the more resources you throw at it. But people, I think, are kind of forgetting the golden rule when it comes to machine learning, which is that, it's not the size of the model that matters, it's how you use it. Or more technically, you should always try to pick your model based on the problem you're trying to solve and the resources you have at hand, not just always assume that, more resources is going to lead directly to a better model. So, um, on that topic, a few weeks ago, I talked about XGBoost, which is kind of the most popular version of a gradient boosting tree model. These types of models are, supervised, non-parametric, and can be very effective, especially when you use them on GPU for both training and making predictions. And in this video, I want to talk about CatBoost, which is an alternative to XGBoost. It's also a gradient boosting tree model. It's sort of an alternative to XGBoost that's been getting a lot of traction recently for prediction tasks, particularly in finance, but it can be applied in other places as well. So, with that said, let's go over some of the technical background. Specifically, what are the three key differences slash similarities between CatBoost and XGBoost? If you want to learn more about XGBoost, go back. You can go to my channel and find a video on that from about 2 weeks ago. So, um, let's start with the biggest difference, which is that so yeah, here are the three differences. There's categorical encoding, symmetric versus depth first, tree building, and then minimum variance sampling. I'm going to explain what all those are. So let's start with encoding, which is kind of the biggest difference between CatBoost and XGBoost. CatBoost actually stands for categorical boosting. It has nothing to do with cats inherently. Um, but what does that mean? So decision tree based models, to build them, you're going to actually have to calculate the gradients at every uh, boosting step, which means that all of your inputs in training have to be numerical so that you can actually calculate the derivatives. And in the real world, most of the time your data isn't going to be numeric. You're going to have some categorical features like what city someone lives in, or what day of the week is it, or what gender are they, those are all can't they're not represented as numbers, which means you need to encode them as numbers in some way. So when you're using XGBoost, you actually have to do that encoding yourself before you train the model. And CatBoost's biggest advantage, I think, is that it actually handles this encoding inherently. The model will make the encodings itself using something called ordered target encoding, which is more effective than one-hot encoding. And that just means that you can give it your data and the model will figure out how to train even when there's a mix of numerical and non-numerical uh, predictive features. So this is very good for high cardinality features, like when you have categories with a lot of different types. Like when you're talking about someone's gender, it's either, man or woman. So that's not very hard to encode. But if you have like all of the cities in the US, every city is going to be a unique string, and that's there's a lot of different strings, which makes it more challenging to encode. And that's one huge benefit that CatBoost excels at compared to XGBoost. But it's also slower on training on larger data sets. That's going to become very evident at the end when I actually try to run these two. But let's talk a bit about what ordered target encoding is. So, when you encode data, you can use something like when you try to encode like a string that's not number, you can either use something called one-hot encoding, which is basically a vector of ones and zeros, or you put a one every time at a position that represents that word and zeros everywhere else. That's kind of like the default go-to way to encode, but it's not always the most effective. Another approach is called target encoding. That's where you actually come up with an encoding for a word based on the frequency it appears with your target variable. I'm not going to go too much into what that means, but basically, like, you see what the association is with the target output that you're trying to predict and the categorical features, like how often those two appear in pairs. Well, that's a smarter way to encode, but it has a problem known as data leakage. So if you're going to encode based on the frequency distribution of, your predictive features and also your target, which is what you're trying to predict, you're going to be making some assumptions about your data based on data that it's not supposed to see. So you're basically making encodings based on your entire data set, which is what you're trying to predict. So there's some kind of cyclical logic here, and that's known as data leakage. Well, CatBoost handles this. So they do target encoding for the categorical features, but they do it in a way that's ordered. What that means is that they're splitting up the data into chunks or what they call folds and only building these encodings based on the points that came before it in the fold so that you're not actually making this encoding based on unseen data. Um, and I'm not going to go into full detail on, the algorithm or how that's implemented. Here's sort of like the high level pseudocode on the left. Um, or actually, no, this is for ordered boosting. Sorry. So once you have your ordered target encoding, you can't just apply normal boosting to, I mean, you can, but that's not what CatBoost does. Their actual boosting algorithm for building the trees iteratively is known as ordered boosting. And it uses a similar approach as what we talked about with the ordered target encoding, which is that it's going to split up the data and reshuffle it for every tree and only train on points up until point I in your permutation, so that you're not training on like out of sample or gaining some knowledge about your data that you shouldn't be getting. This is sort of the pseudocode of how ordered boosting works on the left, and this on the right is sort of like on the top would be use your whole data set, training data, to build every tree in the boosting process. This would be like what XGBoost does. Whereas on the bottom, you kind of reshuffle, create permutations every time, and train only up until a certain point in that permutation. That's what CatBoost does. And as you might imagine, that is slower than normal boosting, but it's supposed to reduce overfitting and reducing noise in your model. So the idea is that the improvements are going to outweigh the negatives for the performance. The improvements in the quality of the predictions are going to outweigh like the negative performance loss. So, even though CatBoost, so it does, like we said, it encodes using the ordered target encoding. It builds the trees using ordered boosting. So those are two big differences. And then another difference between CatBoost and XGBoost is that CatBoost builds each of its trees symmetrically. What that means is that your tree is always going to be balanced, and that splits are going to happen on both sides. It's going to be the same split on both sides of your tree every time there's a split being made for a feature. So, whereas in XGBoost, it might create like any type of tree that's not ordered, and like you see, if you try to balance that tree, the first step would be like what XGBoost might build, and then CatBoost would have like a symmetric tree. So What are the why would CatBoost do that? What are the advantages of building symmetric trees? It sounds like we're just making splits for no reason. Well, there's a couple of reasons that CatBoost uses to justify this decision. The first is that it gives your model faster inference speed since you kind of know beforehand what your tree structure is going to look like. It also makes the calculations more efficient in parallel since your tree is going to be balanced. Um, and also, if you're trying to do any type of search or traversal on that tree, it's always going to be logarithmic because it's perfectly balanced instead of, what might happen in this case on the left where it would be like a linear situation. Um, so, and it's also supposed to contribute more, most importantly, going to contribute to the overarching goal of, CatBoost, which is to reduce overfitting and kind of create like more ordered model based on your mix of categorical and numerical inputs. Um, and the last big difference, so yeah, what did I talk about so far? It's talked about the encoding, the boosting, symmetric versus depth first tree building, and the last point is minimum variance sampling. So, what is that? What is sampling, first of all? Sampling is when you want to train on a random sample at each boosting step. So, if you'd watched my XGBoost video or if you know how boosting works, you're building a new tree at each step iteratively to try to reduce the loss of the previous tree. So, you're kind of learning sequentially. Well, every time you build a new tree in that iteration, you're not going to build it on the entire data set because it's really costly. So what we do instead is something called sampling. That's where you take like a random sample of the data and assume by, the law of large numbers that this sample is going to be representative of your whole data set. So it's kind of like sampling when you go to a store like Costco, like they're going to give you some food to try it, and that's going to give you an idea of like what the thing tastes like, even though you didn't eat the whole thing. Um, Kind of a dumb example, but I think it gets the point across. Well, how does XGBoost and CatBoost handle sampling? Well, XGBoost uses uniform random sampling, which means just purely random sampling data with same probability. And CatBoost uses something called minimum variance sampling. Don't get this confused with what we talked about in ordered boosting, where we're reshuffling the data and only training on permutations. That's a separate issue. Like that, this reshuffling and training on permutations, that's not considered our sample. The sample would be once we reshuffle, create this new permutation for each tree, then on that permutation, we're going to take a sample of that because we're not going to train on the entire permutation. That's still going to be too costly. So, how does minimum variance sampling work? Well, we want to sample the data intelligently instead of uniformly to sample data with high contribution to variance more often. The assumption is that samples with larger absolute gradient contribute more to the overall variance of the model. So, what this means is that we're going to try to sample training, like training data, like different instances of training data that contribute more to the overall variance. The idea is that these points, which contribute more to the overall variance of the system, these are going to have more meaning, and it's more worthwhile to try to learn from these data points than from ones that don't contribute much to the variance. Um, so what that means is that for each item in our training set, which we call a sample, we're going to assign it a sampling probability based on its contribution to the overall variance, which is calculated from its absolute gradient. That's the bars, the G sub I in the bars. That's the absolute gradient of the sample divided by the total absolute gradient, the sum of absolute gradients of all the samples. So it's a pretty simple calculation. That gives it a probability pi that add up to 1. And we're going to be sampling the data points with higher pi. So this pi actually represents what's the likelihood that we're going to sample that data point. And obviously, if something has a higher pi because of a higher variance contribution, there's a higher chance it's going to be sampled. All right, so I hope that gave you a good concept of the similarities and differences of CatBoost and XGBoost technically, and also you might be able to infer like where you might want to use each model what scenarios would be best. The key idea is that CatBoost is supposed to be like easier to use and that it will encode the variables, your categorical variables for you, and that CatBoost is going to kind of try to use intelligent sampling and preventing data leakage to reduce overfitting and noise in your model. But XGBoost is supposed to be like more versatile and it'll just, make the decisions wherever, regardless of what that impact might be on overfitting potentially. And that XGBoost is going to be a lot faster since it doesn't have to create random permutations and do intelligent sampling at every boosting iteration. But anyways, without further ado, now I'm going to get into sort of like the Python tutorial for how to actually implement both these models and train them on your GPU and do hyperparameter tuning. So let's get into that. Alright, welcome to the tutorial part of the video. I'm going to be doing this, I'm on my Linux server right now, but I'm going to be doing this in a Jupyter notebook in Python. I'm going to try to go step by step, but obviously I can't cover everything. Um, so the first thing you should do, I don't know if this is like 100% necessary, but I'd highly recommend that you create a Conda environment. I'm doing this, I'm at a Rapids 24 environment. That's NVIDIA Rapids, which is sort of like the library for connecting your GPU to like Python data science tasks. I'll put a link in the description of this video for the site you can go to see how you actually set that up. Yeah, and for the data set I'm actually going to be using, this is a housing data set. It's a Kaggle regression competition. I think it's active right now, but basically what we're going to be trying to do is predict the household income for a house given some predictive features. So let's drop the nulls there. Here we can see what our data set kind of looks like. I'm going to show the head to get the idea. So as you can see, every row we have like the person's age, education level, occupation, dependence, all this stuff about what a person's life, and at the end we're going to try to predict their income, which I think is kind of a funny task, but should be interesting to see like what features contribute most to a person's income, I guess. But like I said, when you're doing these types of problems, you can see right here there's a mix of numeric and categorical features. Like number of dependents, that's clearly going to be a number, but occupation, you can't really represent that as a number very simply. Like with married or single, you can just use, 1 or 0, or like a vector of 0 and 1. Um, but for something like occupation, where there can be a lot of different occupations, there's high cardinality, so that's kind of harder to encode. Let's print what the non-numeric columns are. That makes sense. And like with every training set, you're going to want to split it into training and testing data. I think that's pretty obvious. The target we're going to be trying to predict is income, so that's going to be our y vector. Um, so yeah, once you have your data set loaded in and you set up your environment, make sure to import um, XGBoost regressor and CatBoost regressor if you're doing a regression task like we are. This is how you import these libraries once you have your environment set up. And once you have that, what we're going to do also is something called a grid search function. What that is for every model, you have your model. We talked about the logic about how these gradient boosting tree models work, but there's also some ways to tune a model. So not every model is going to be exactly the same. There's going to be some parameters that are slightly different. Like we can adjust the maximum depth of our trees, or what the learning rate is going to be, or what's the minimum, amount of iterations, or the maximum number of iterations that we want to do in our boosting step, in our boosting process. So these things that we tune, those are called hyperparameters, and you never know what the optimal combination of hyperparameters is. You can try building like one model at a time, training it, seeing how it does, and then trying to improve by like changing the hyperparameter combinations. But the smarter way to do that is doing what's known as a grid search. So I'm going to try to include that in the video too, just to try to give you as much knowledge as possible. So we're doing this on GPU, we're doing automatic hyperparameter selection. Um, and yeah, so how to do this, basically you want to set up your grid of hyperparameters. So these are all the possible different values we want to take to test out for every model. Um, you want to import the randomized search CV from sklearn and define a number of iterations. So with our n iter equal to 25, basically what this function is going to do down here is create 25 unique combinations from this grid. Um, you can have this equal to whatever you want. Like you can have this be 4,000. Like there's probably around 10,000 different combinations of all these different values that I have here, but we're only going to do 25. And you give it some type of performance metric, which is going to be root mean squared error, which is pretty standard for regression tasks. And basically, it's going to return which model had the best RMSE, what parameters created that, and then it's going to return the model itself so you can use it. And I'm going to do that for both my CatBoost and my XGBoost. To train your CatBoost, you want to make sure you set the task type equal to GPU, and then decide like how much of your GPU you want this to use at max, like which I set as 0.5. And then for XGBoost, I talk about this in my video about how to run this on GPU, so go watch that to get the full in-depth explanation. But you basically need to set up D matrices for all of your training data and set the device to CUDA. But I'm not going to explain that because I already did it in a past video. Another important thing, when you're going to do something on your GPU, first of all, make sure that you actually have a GPU. I know that seems dumb, but a lot of people tend to forget that or overlook it. Make sure your GPU actually has memory available. So it looks like I do have a GPU and it's got a lot of memory free, which is perfect. Now I set up my data set. I set up my grid search functions. We're going to try out 25 different models for both CatBoost and XGBoost, and we'll see how it does. First thing I should mention though is I commented this out, but if you actually want to run XGBoost on the data we imported, it's not going to work. See what it says. Data must be int, float, bool. Yeah, you can't. So XGBoost can't handle non-numeric features by itself, but CatBoost can, and I'm gonna run it right now. Last time it took around 10 minutes for 25 different models. I'm gonna pause the video and get back to you once it's done. Alright, so we're back now. This actually took a lot longer to train than I thought it would. I was expecting somewhere around 10 minutes, but it actually was closer to 25 for 25 different models. That adds up to about a model per minute on a data set of around 10,000 data points, which isn't bad, but it could be better. Like I mentioned in the technical background of how CatBoost works, it has to handle the encoding. It's going to do ordered boosting, and it's going to do minimum variance sampling. All those add extra overhead when it comes to actually, training the model, especially the ordered boosting where you have to, get a different permutation of training data points every time you're actually boosting a tree iteratively. So that explains why it took longer. We can see what the actual performance is here. And like I said, we did handle hyperparameter selection too at the same time, which is a huge plus. You can call the .get all params to see what those actual hyperparameters are for your best performing model. And now let's get into actual XGBoost. Like I showed, it's not going to work if you actually pass in the data directly because there's categorical data points and you have to encode those manually. That's one big drawback compared to CatBoost, which will handle this innately. But if we want to do encoding, there's two kind of approaches. You could do one-hot encoding using the sklearn.preprocessing function. That's probably the easiest bet. That's what I'm going to do in this tutorial. You could also do label encoding or also do target encoding like I talked about in this video as well. That could maybe boost your performance. I tested those out earlier and I didn't see much of a difference, so just for simplicity's sake, let's do the one-hot encoding. What you're gonna want to do is create, the dummy variables. I actually don't think I used the one-hot encoder here, actually. I think I just used the pd.getDummies. But it's the same idea. It's the same concept. That just creates one-hot encoding for all of your non-numeric columns that you specify. And once you have the encoded data, you're going to you're going to split those, and then you're going to call the XGBoost, train it on the encoded data. As we can see, that just did 25 trees in less than a second compared to around 25 minutes for CatBoost. So I was expecting, XGBoost to perform better, but this is pretty shocking. I didn't expect the difference to be this drastic. They're both using the same GPU on my server. So yeah, clearly XGBoost is much faster. You've got to handle the encoding yourself and do more data pre-processing, but I think even with that, even if you do this from scratch, it's going to be faster to just train an XGBoost model. And I assume that this performance boost is going to be even more amplified the bigger your data set gets. So 10,000, it's not small, but it's not very big either when you think about real world applications. Um, this is how you print I think this is how you actually print the hyperparameter, um, what parameters were selected for your best performing model. So I'm not going to go through those, but that's just how you see that. Let's compare the results now. So here are the XGBoost results for the best performing model, and and then the CatBoost. So we can see that neither of them did well. R squared is very low. I'm assuming, oh, this is because, we didn't actually do any feature engineering or actually much pre-processing at all on the data set. I kind of skipped over that just because that's not the point of this video. Um, Another reason why is since we're predicting household income, if you think about it, some people are always going to be getting paid way more than you can logically explain with a good model. So there's the largest error. Someone's getting paid $9 million more than we expected. So these types of very large errors are going to, skew our R squared and make it look like the model is performing really poorly. But if we look at both of them, it does seem like CatBoost did better. Its R squared is more than twice that of the XGBoost, and both of them have in the largest error that's pretty high. So we could say that the CatBoost actually performed better in terms of just R square and also, RMSE. CatBoost is also lower and on the mean average error. So all those metrics point to the CatBoost being better. Um, but again, it was how many times? Like 600 times slower. Way more than that actually. Many orders of magnitude slower than XGBoost. Let's look at one last thing that would be useful is also just to see like what different features were selected as most important by both of these models. This will give us kind of an interesting comparison here too. So it looks like XGBoost, when we're doing this, importance is by the number of splits. So it looks like even though CatBoost is supposed to be more regularized in theory, it looks like the CatBoost actually made more splits, which is interesting. I think this might happen because XGBoost probably selected a hyperparameter for to make the trees more confined and more regularized. But it's not a huge difference. The top feature here gets an importance of 20, which is twice that for XGBoost. Work experience were ranked as most important here. Home ownership status, so like if you're renting or actually own the home. Urban location, whereas over here we have just the location, the work experience, and status. So what this means is based on what the models have decided for feature splitting, these are kind of the three most important factors in your life if you want to like predict what your income's going to be. So if you didn't learn anything about, tree boosting models like XGBoost or CatBoost from this video, well then I hope at least you learned about what you need to do, move to an urban location and get a lot of work experience, and then your income will be high. Although I'm sure you could have figured that out without machine learning. But anyway, with that said, I hope that this video actually, taught you something about how these boosting models work, what the different variations are. CatBoost can be very powerful and outperform XGBoost in some scenarios, like we just showed, but it's going to be a lot slower. So if you're trying to work with like real-time data on very large data sets, then XGBoost is probably the better choice. Whereas CatBoost, if you need to make more, higher accuracy predictions and you're working with high cardinality categorical variables, and that's probably the better choice for you. But anyways, thanks for watching and stay tuned for more videos.